Hello and welcome to the course Signals and Systems. I am Dr. Zishan Kalim from Electrical Engineering Department, CUIUA campus. In this video, we will cover the contents DTFT properties. Let's start and discuss properties of DTFT. As with the continuous time Fourier transform case, a variety of properties of DTFT provide insight into the transform, and they are often useful in reducing the complexity and evaluation of transforms and inverse transforms. For example, you have a signal x of n, and whenever you take the Fourier transform, you can get x e j omega. So the x e j omega is used to represent the discrete time Fourier transform. And if you have a given the Fourier transform signal, for example x e j omega, and you have to find the inverse of that signal, that is called inverse Fourier transform, then you should take f inverse. So f inverse is equal to x of n. In this way, you can get back the original signal x of n. So x of n Fourier transform is x e j omega, whereas x e j omega inverse Fourier transform is x of n. The first property is the periodicity of DTFT. As we already discussed that the Fourier transform DTFT, discrete time Fourier transform, is always periodic in omega with period 2 pi. What does it mean? It means that uh, the after the period of 2 pi, for example j omega plus 2 pi, it will repeat and it will be exactly similar to the x e j omega. Whereas for the continuous case, it is generally not periodic. Linearity and of the Fourier transform. Linearity, it means that if you have, for example, signal x1 of n, its Fourier transform is x1 e j omega. And if you have a signal x2 of n, its Fourier transform is x2 e j omega. Now, if we want to combine them and add them, for example, and multiply by some constant a, then ax1 plus bx2, whenever we take the Fourier transform of this signal, then it should be equal to ax1 e j omega plus bx2 e j omega. So this satisfies the linearity property as well. The other one is the time shifting and the frequency shifting. Let's discuss first the time shifting property. In time shifting, for example, if you have a signal x of n, and whenever you take the Fourier transform, it will give you x e j omega. And what is time shifting? In time shifting, for example, instead of n, you have a n naught, any n naught time delay or advance, right? So x n minus n naught. So what will be the Fourier transform? It will be e minus j omega n naught. N naught is this n naught x e j omega. So the time delay brings the phase shift in the Fourier transform signal. In frequency shifting, whenever you multiply the x of n with some different frequency omega naught, so what will happen in the frequency after taking the Fourier transform of the signal, you will have a frequency component at omega naught, right? It is shifted at omega naught. So previously it was at omega, for example, then it shifted to omega naught. So carrier frequency is shifted. So the Fourier transform is x e j omega minus omega naught. So omega minus omega naught represent your original frequency is shifted to the omega naught. The other property is conjugate and the conjugate symmetry. What does it mean? For example, xn is your given signal, and whenever you take the Fourier transform, it is x e j omega. It is general. So, in case of the conjugate of a signal, if you take x conjugate of n, the given signal is x of n, you take the conjugate, and whenever you take the Fourier transform of this conjugate signal, you will get x conjugate e minus j omega, right? So, also when xn is a real valued, so whenever the xn you selected is a real valued signal, so what will happen? Its transform x e j omega is conjugate symmetric. What is conjugate symmetric? It means that x e j omega is the Fourier transform, so it is equivalent to x star. X star means x conjugate e minus j omega. So they both are equal. So x e j omega is equal to x star e minus j omega for the case when xn is real. From this it follows that the real part of x e j omega is an even function of omega and the imaginary is an odd function of omega. Similarly, for the magnitude of x e j omega is an even function and the phase is an odd function. So E1 of x of n is equal to real x e j omega. Odd of odd function is j imaginary x e j omega. So where even and odd are the even odd parts of the x of n. So whenever you divide the signal into two parts, one is the even part and the other is the odd part. So the Fourier transform of even is real, whereas the Fourier transform of the odd is imaginary. Right, this one. For example, if xn is real and even, its Fourier transform is also real and even. And if xn is not real and even, then its Fourier transform will also be imaginary, right? So this was the conjugate and the conjugate symmetry property. The other important property is differencing and accumulation. As we already discussed in the continuous time case, uh, where we have a integration. In continuous time case, we have a integration, whereas in a discrete time counterpart of integration is accumulation. So accumulation and integration meaning more or less same. However, the term integration is used in the continuous time case, whereas for the discrete time case we use the term accumulation. And its inverse first differencing. So for uh, and its inverse discrete time counterpart of integration is accumulation and its inverse is differencing. Let xn be a signal with Fourier transform x e j omega, and then from a linearity and time shifting properties, the Fourier transform for the first difference signal is, so difference signal is equivalent to integration or differentiation, whereas accumulation is equivalent to integration. So how to find the difference of a signal? By using the time shifting and the linearity property. So according to the time shifting property, for example, xn minus x minus n minus 1 is given by, so xn minus x minus n1 n minus 1, if you take the Fourier transform, you will get 1 minus e j omega x e j omega. How you will get? Let's see here. So differentiation is only possible for continuous case. Differentiation is only possible for continuous signal, whereas we will focus on differentiating in discrete case. So whenever the signal is continuous, you will take differentiation. Whenever the signal is discrete, then you will take differentiation. Okay, let's see how it looks like. For example, xn minus x minus n minus 1. So xn Fourier transform is x e j omega, right? And by time shifting property, x n minus 1 Fourier transform is e minus j omega x e j omega. We already proved in the previous slide. So by taking the difference by using linearity and the difference property, you will get x e j omega minus e j omega minus omega x e j omega. So by taking x e j omega constant, you will have a 1 minus e minus j omega x e j omega. Similarly to this equation. So whenever instead of a 1 you have a constant and not here, so that generally this equation can be written in this way: 1 minus e minus j omega n naught into x e j omega. So this is differencing property. The other property is accumulation. Accumulation is similar to integration in continuous time. Okay, let's see how it looks like. Accumulation means that you have to add the different time signal in different with different times, right? Discrete time. So, for example, accumulation yn equals to summation m is equal to minus infinity to n for x of m. So, if we can write them break into two parts, how it means that instead of n, if we say that it's n minus 1, right? N minus 1. So, one term we separated, it is xn here. So, you know that if you subtract 1 from x of m, this one, so it is equivalent to yn minus 1, because yn is equal to x of n when we accumulate all the terms. When we take out one term, so it is equivalent to yn minus 1 plus x of n. So rearrange these terms. So yn minus yn minus 1 equal to x of n. By using the time shifting and linearity property, we already proved it is equivalent to 1 minus e minus j omega y e j omega when take the Fourier transform. And its Fourier transform is x e j omega. So just rearrange y e j omega is equal to x e j omega 1 minus e j omega. So this is the accumulation property when the condition is if x e j 0 is equal to 0. However, this is not a complete equation. To write a complete equation, it is equivalent to y e j omega x e j omega 1 minus e j omega plus pi x e j 0 summation minus infinity to infinity delta omega minus 2 pi k delta omega minus 2 pi k. Here we need the additional delta function. Why we add this function? The reason is that if the average of the given signal is not 0, if the given signal average is not 0, then the resultant signal will grow and the output will continue to grow. So to stop that growing uh, and to make this average 0, we have to add this additional term, right? The other property is the time reversal. Time reversal means that if xn is given signal and its spectrum is x e j omega, spectrum is the Fourier transform, and if you consider the transform y e j omega, then for the yn equals to x minus n, if your signal is x minus n, so put here y e j omega n is equal to minus infinity yn e minus j omega. Instead of yn, put x minus n and e minus j omega. Let m equals to minus n, so substitute this, so you will get xm, and instead of n you will put minus n here, so it is minus j omega m. So it is equivalent to the difference between x e j omega and x e minus j omega is here the negative sign. So it is equivalent to x e minus j omega. So it means that whenever you take the transform of a time reverse signal, you will get x e minus j omega instead of x of j omega. Okay, let's discuss the summary of the properties of DTFT. Linearity we studied, and if you have a AXN, BX2N, so in Fourier domain it is AX omega, BX2 omega. And time shift or delay xn minus n, it is equivalent to e minus j omega n x of omega. And frequency shift x and e j omega cn, it is equal to x omega minus omega, right? So linear convolution, if you convolve the two signals in the time domain, it is equivalent to x omega h omega in the frequency domain. In modulation, if it's x and pn, it is equivalent to 1 over 2 pi from pi 2 pi x omega minus n dn. Same for the periodic signals, xn is equal to n xn plus n, and we already proved that the discrete time Fourier transform of periodic signals is 2 pi ak delta omega k omega c. So here the terms, maybe the notations will be different, the meaning more or less are the same. Thank you for listening, and for Q&A session, we have an online separate session. Thank you very much.